In other words, when you are particularly dealing with a Centuri reaction, if you have an interposition where it's attached, therefore the reaction will be much slower. If it is open, and therefore we see a very distinct difference of metal versus primary, and then the secondary actually doesn't work very well. Okay, secondary works, but tertiary is almost much slower. So the steric effect is important. The second thing, we also discussed something that is new with respect to now that we can introduce the stereochemistry, is that it undergoes an inversion of configuration. With respect to the Centuri reaction. In other words, in many cases, there will be inversion, but we wouldn't know about that because, let's say, if you have a metal group, the hydrogens are inverted, but that would make any change in the stereochemistry. But when there is a stereochemistry involved, and if it is tidal, then you will see the effect of that. So those are the two important things that we discussed. And just to give you an example, there is a problem in your text that asks you to come up with the solution of this, telling you essentially that you have this compound reacting with 1,4-dimethyl. So the reaction that they're talking about is this one. And they're also telling you that it undergoes actually a Centuri reaction, and one will be the product. Now, when you look at this reaction, again you have to see what is okay. So one would be the nucleophile and one would be the substrate. In this particular case, the nucleophile is the first molecule, and the most nucleophilic side is N minus because it's a potassium salt, so it really remains as this. So the nitrogen is going to attack the bromine, and now you have two different bromines. So now you have to decide where it's going to attack, 1 or 4. And as you can see, that there is a huge preference of attacking at the 1 position, which is primary, whereas the 4th position is secondary. Right? So this is primary, and this is a secondary position. And primary has a huge advantage over that. Therefore, the way this reaction will go is that it's going to attack this and pick out the bromine, and you end up getting the resultant product. Plus okay, so this is the major organic product, and of course this is actually part of the synthesis scheme. It undergoes other reactions later on. But essentially, the point of this exercise is that you need to find out which one is the nucleophile and which one is the substrate, where it's going to attack, because there are a couple of different options out there. Okay. Now, moving on to those discussions, now let's talk about a little more about nucleophiles. Let's talk about the term nucleophilicity. Nucleophilicity has a relationship with bases because they're all Lewis bases. So the nucleophiles are Lewis bases. In some cases they are, but in many other cases they would be different. And how do we know exactly what the nucleophilicity order? And there are some clues as to how we can determine that. One would be looking at the periodic table. And so let me start with periodic table and write carbon, nitrogen, oxygen, fluorine. Okay, so same row. When we look at that, then we can come up with some of the nucleophiles involving each of these elements. Okay, so let's say you have F minus versus OH minus, NH2 minus, and CH3 minus. When we look at them, we can see that the basicity order, basicity is actually decreasing in this order. So it's actually increasing in this order. Basicity increasing. And at the same time, nucleophilicity also increasing. Same order. They are going in the same direction. Now, we can also look at each row and then determine how that yields. And we can look at the halogens. You have, let's say, chlorine, then chlorine, bromine, and iodine. And again, the relevant atoms that you can think of is the nucleophile would be F minus, Cl minus, Br minus, I minus. Now, we can see that as we go down, nucleophilicity increases. Significantly in this order. Okay? In other words, iodine I minus is a better nucleophile than Br minus, and Cl minus is better than F minus, and so on. Okay? But the basicity is now reversed. The basicity is actually decreasing in this order. Likewise, we can also look at other cases. Here, so far what we described, each one has a unique negative charge. And of course, you want a nucleophile to have a negative charge. That works better because the excess electron favors attacking something that is positively charged or even partially positively charged. That's how the nucleophilic reactions happen. But there are also neutral nucleophiles. And neutral nucleophiles but electron rich. Those are the kind of situation that we can also consider. And if we consider that, then we can also look at periodic table. Let's say if we look at oxygen versus sulfur. So let's look at H2O versus H2S. Since we are going down, we have seen, as in the case of halogens, that nucleophilicity increases. So again, we can see that the nucleophilicity increases in this order. In other words, H2S is a much better nucleophile than H2O. The same way you can look at nitrogen and phosphorus. Okay, if we look at NH2 minus versus PH2 minus, that is the phosphorus is a better nucleophile. So those orders are relatively easy to figure out. However, it gets complicated when you are looking at some other cases. Like let's say if you look at cyanide and azote and P minus. So this type of approach will not work. Then you need to figure out what would be the basicity of that, and then also figure out, compare with the other, how the nucleophilicity will change. And as a rule of thumb, as I mentioned before, that we have separate groups of nucleophiles. That some of them are good nucleophile group bases, some of them are good nucleophile and weak bases, and so forth. I gave you a table. So you kind of have to familiarize with that so that you can figure it out. Some of them really work towards the good nucleophilic reactions. All right. Now, even when you are doing with this, let's say, looking at a reaction, with a neutral mode, such as water, reacting with methyl iodide. So water is a relatively poor nucleophile. It's not a great nucleophile. This reaction will be much faster if you have an OH minus. So we can compare the two reactions. The second reaction is much, much faster. And that, of course, relates to a high electron density on the oxygen in this one. So it can act as a much better nucleophile than water itself. Okay. And so you will generate CH3, which in this case. And in the other case also, it can attack at much slower rate. And it can still generate the same product. But it goes through two states. In other words, it will form, the initial state would generate the proton index species, okay, at plus I minus. And then that is going to be picked up by another molecule of water. And then you get the methanol. Okay, plus H3O plus I minus. So this is therefore a much slower reaction, but nevertheless, that can still undergo this reaction. And now we can carry out this reaction with another group, and then the mechanism will completely change. This is still an SN2 process. Both of them are SN2 process. The second one is a lot faster and compared to the first one. But now we change the reaction, and what we do, rather than now the mechanism completely changes because H2O is not a strong enough nucleophile to displace, and with a tertiary carbon, this is going to undergo initially a bond breaking between the carbon and iodine. So it generates a carbon cation. Now the water attacks and goes through the process, and it initially generates OH2 plus, and then the hydrogen is picked up by another molecule of water. This process is essentially similar, and I'm just writing the final product where you have generated the corresponding alcohol. But now the reaction has changed to SN1 because this is the rate determining state, and formation of the carbon cation, which does not involve the water, and this product is formed. Now, both of these reactions, there is a general term for them. What we call them is, even regardless of whether it's going through SN2 or SN1, these reactions are called solvolysis. What it means is that the solvent is acting as a nucleophile in this reaction. But the mechanism could still be very different. The first case, we showed that you need the water because it's a primary carbon cation is very difficult to form, very high energy, and therefore it needs the assistance of the water to displace the iodine, and then it it undergoes the reaction to the final product. And in the second case, it goes through an SN1 process where you generate the carbocation first and then it's undergoing the reaction. Now, again, as we mentioned that the H2O and OH has a big difference in nucleophilicity, we can also see that similar cases can happen wherever the molecule is very stable, it's relatively weak nucleophile. That is given when you compare the H2O with OH minus. The same thing happens between ammonia and H2 minus. This is a much better, stronger nucleophile. Likewise, we can see that sometimes resonance stabilization can do that as well. If you look at an alkoxide, RO minus, versus RCOO minus, this is resonance stabilized, and therefore it's a weaker nucleophile. In other words, if you have a nucleophile and you compare them with another one, whichever is the more stable one by itself, regardless of whether it's a neutral molecule or an anion, that is a weaker nucleophile. It doesn't want to attack. It's already happened the way it is. Okay. So the nucleophiles are typically electron-rich species, okay, which is relatively unstable and wants to attack something to generate a more stable structure. Now, as we started discussing the SN1, we didn't so far discuss the stereochemistry of SN1 reaction. Now, theoretically, this is what is supposed to happen. The reaction we discussed, like with the SN2 process, is something like this. Let's say we have discussed this reaction in the SN2 process. It's a secondary carbon, therefore it can undergo, it's kind of intermediate, and therefore it can undergo both SN1 or SN2 depending on the conditions. If you have a good nucleophile here, then it's going to undergo SN2. But if you provide a solvent and undergo a solvolysis reaction, then it is going to undergo SN1. So let's do that rather than using the OH minus or an alkoxide or anything. Let's put an alcohol there. So let's just see OH, methanol, which is a poor nucleophile. And this nucleophile is not able to attack by itself, and therefore the first step in the process would be formation of a carbon cation, where the bromine would break from the carbon, and we get H, CH3, CH2CH3, plus Br minus, plus methanol is there, which is the solvent. Formation of the carbon cation. Now we can see that the bromine, now the methanol is going to attack and form a methoxy compound. So the final product would be two things. One would be this is a hydrogen. sp2 hybridized, sp2 carbon. And this is chiral, sp3 carbon. So in this case now, because the intermediate is a chiral, theoretically we should also get a chiral product. we should get equal amount of this is what we should get theoretically. That's not what happens. Most of the time in a reaction like that, what we see is that it's a partial recipe product because we get about 90% of the inverted product and about 10% of this product. And these numbers will change depending on the condition of the reactions. Why? One of the reasons is that even though you broke the bond with bromine, the bromine did not actually leave the site. So while the solvent is approaching you, they have much better access to attack from the other side. So most attack takes place. Even though you form this, is one part of this is blocked by the bromine, and therefore it attacks from the other side. Most attacks take place from this side. And as a result, you get a predominantly inverted product, whereas the retention of the configuration happens in a small part of the molecule. So, in other words, the SN1 is a significantly more complicated situation where we generate an ion pair, and because the ion pair is not completely dissociated, and it is also related to the lifetime of the carbocation that is formed, we get a partially inverted product. And of course, you are familiar with the energy diagram of this reaction, where you would go from initial starting material of the RBR, going to the first state, which is formation of the carbocation, and then goes to the formation of the alkoxide, finally you get to the final product, RO. In this case,